Okay, so good morning everyone, Senan this side, and in this video we are going to see how to solve this binary tree post-order traversal, right? So I would show you two ways. One is the normal recursive way and the other is the iterative way. And I would go through two dry runs of each of the methods, and be sure to watch it till the end to understand this topic in. So what is the post-order traversal? So post-order traversal is basically telling first process the left subtree, then process the right subtree, and then process the root. So first go to the left, then go to the right, and then process the root itself. So if you look at this case, so first process the left subtree. There does not exist a left side of this root. So then we process the right subtree. So what is the right subtree? Is this 2 to 3 is the right subtree. Now what do? Now you process the left, then right, then the root itself, right? So over the left is 3, so you push that as your answer because it does not have a left child or a right child. That means we have to now process the root itself, 3. Now I go back to 2. I see for the right child there is no right child, right? So I've done with the right child. So I now process the root of this subtree, which is 2. So I get back 2, 3, 2 as our answer till now. Now for this root node, I've processed the left subtree, which is null basically, and then we have processed the right subtree, which is this 2 and 3. Now we can just process the root of this, so 3, 2, 1. Now for an empty list, we return back empty tree. So basically this is an empty tree, so we return an empty tree. If we have a single node, we return that single node itself. Okay, so the number of nodes is within this range and the value is as in between -100 to 100. Okay, and recursive solution is trivial. Could you do it iterative? So we'll go over both of these solutions, and let's see our notebook for the very first example. So here we are in my notebook, and as you can see, we are going to do this by two approaches. The first one is recursive solution and the second one is the iterative solution. I've taken these two examples. This is what was given in the problem, right? And this is a random tree, binary tree that I just generated. So let's look first at the recursive solution, and once you understand this properly, we'll go over and look at the iterative solution again on these two examples itself. Okay, so here is the recursive solution. So what does the post order traversal say? First evaluate the left side, then evaluate the right side, and then in the end evaluate the root. Okay, so that is what we are going to do. So first of all, we reach at this position, the 1. Now what I have to do is I have to process this subtree first, then this subtree, and then in the end I return or add 1 to my answer. So let's do this for this subtree. So again, now seeing this 2, I would first process the left, then process the right, then process the root itself. So now let's go and process the left side. And if you see, we are at a leaf node, which is basically it does not have any child nodes. So there is no left, there is no right. So that means we are vacuously done with processing the left and right child. Now I can just process the root. So what I would do is I would take this 4 into my answer. Okay, I'm done with this. So now let's process the right subtree of this. Okay, now I see a 5. I see this subtree, right? So this is the root for this subtree. So I need to first process the left side, then process the right side. Let's go and first process the left, and as you see, the left is 6, and since this is the leaf node, we are vacuously processing the left and right because there is nothing to process. And what I do is I just take that 6 into my answer, and I'm done with the left child. Now I go to see the right child. It does not exist, so now we process the root itself, and what we do is we add 5 to our answer. Okay, now we are done with this right subtree as well, 2. Now since this is done, now we process the root. So what is the root in this case? It's 2, right? And now we are done with processing the left tree of this 1. Now let's look at the right subtree. Okay, so since I see this subtree, this is the root for the subtree. I process the left, then process the right, and then process the root itself. So what is the left? Left tree is this subtree, 7 to 8. Now given this node, I first process the left subtree, then process the right subtree, and then I process the root. So since I'm seeing there is no left child, so we don't do anything. Then we process the right child, and we are having this 8 as a tree. Now if you see, this 8 is a leaf node, which means in a way we have processed the left and right elements. It's basically null. So what we do is we process 8. So what would give us is 8, and we are done with this subtree. Now what you see is we've processed left, we've processed the right. Now we have to process the root. So I take this 7 as an answer, and I'm done with this subtree. Now what I see is I've done the left subtree of this 3. There is no right subtree of 3. So I now process the 3 itself. I take that 3 as my answer, and now I'm basically done. If you see, I have seen the left subtree of this one, I've seen the right subtree of this one. Now I have to process this one, and which is just 1. Now if you see, we have the post order traversal of the tree, right? So if you see, this part is for left of 1, this part is of right of 1, and this root itself, left, right, and the root itself. Now if you observe 4, 6, 5, and 2, this is the root of this left subtree of 1, and this is on the left, this is on the right. Okay, so if you see this, we are basically calling for smaller and smaller problems, the same function. So that is why we are going to use recursion in this case. Okay, so we are basically done. And how do we write this code? Let's say function post order, right? Or given the root, if a root is null, return. Fine. If root is null, return, because there's nothing to do. So what I do is I call post order traversal for roots left. I call the same function post order for this right subtree. Assuming this recursive function is working properly, first you process the left, then process the right, and then you in the end answer dot append root dash value. Okay, so basically this would be your function to do this. And let's look at one more example, this one. So I'll just go through this very fast. So there is no left, there is only a single right. So I process this first. There is a single left, get this 3. I take that 3 as my answer, and then since there is no right, I process the root, which is 2. Now I've done with the left subtree of this one, I've done with the right subtree of 1. I take this value 1 and take that as my answer. Okay, so let's look at the code. So if you see this answer, I created an answer array, pass that to this traversal function. So what this traversal function does is, if root is null pointer, you return, right? If root dot left is null, that means root dot left is a valid node. You go and process the left child. If root right child is null, not null, you process the right subtree and you push that back in. Okay, so basically you are not required to put this if statement, right? Without this would work as well, because if it is null, we just return, right? So you could add an if statement, you can remove this if statement, you're good to go without this as well. So that is the logic. It's quite straightforward. And now we are going to see the iterative version, which actually requires some mental effort to understand, and that is what we are going to do. So let's again look at this example for the iterative solution. I'll keep track of basically two stacks, stack 1, stack 2, right? Maybe the naming would be different in my solution, but so what was the problem in the iterative version? Technically there was no problem. We just wanted a simple answer, because using recursion we can have a simple solution to a very complex problem. But how would you do that iteratively? So you have to somehow keep track of the things that the recursion does for you. And this question is just testing, is that can you visualize, can you analyze what is required, what is being stored behind the scenes using the recursion stack that we are not actually implementing. Okay, so I'll show you the approach. You look at this properly, and after that you'll understand. Well, first of all, I'll take whatever to initialize these two stacks, I'll take the root and I'll that as my answer. So I have 1 in my stack, and that is the initial condition. I'll start with this, right? Now what I'll do is I'll just take this, I'll pop this out and store this into stack 2. Why I would be storing this? Because since we are going down in this tree, right, we need some way to keep track of the parent. Okay, so that is what we are going to do. Or rather than just popping it, let's just pop this, and what you do, you take this one and you find all the children and push that into the stack. So the left child is 2, I push that, I push the right child, which is 3, and I'm basically done with these two elements. Now what I do is I take out the top element, right? I push that into the second stack. So take this 3, push that into this, and now what I do is I find the left child of this top node and the right child of this top node, and I push that into the stack. So then I push 7 into the stack and there is no right child. So I'm done with it. Now since I've pushed this into my stack 1, what I would do is I would take out this element from stack 1, place that element into stack 2, and push all the elements, the neighbors of these elements into stack 1, or the children of this 7 into stack 1. So that in that way we push 8 into the stack, and technically we are done with this. Now what I would do is I pop this out and I push this into stack 2, and since 8 is not having any children, we don't push anything in the stack. Now if you observe, we've somehow processed these 4 nodes and we are still able to keep track of this 2. See, all of these are popped out apart from this. So I'll pop this out, I'll push the neighbors into, I'll push this 2 into the stack 2 first, and then I'll push the neighbors into this, which is 4 and 5. Once I'm done with this, I'll square around it. Now what I do is, if you see, I'll take out the top element, which is 5, and place it in this stack, and I will push all the children of this into our stack. I'll push 6 as well. Now I've pushed this as well. And now what I do is I take this 6 out, I'll push that into my stack, and I'll push all the children of this root, this value 6, into my stack. And since there is no child, I don't push anything in this. Okay, so now we see what we are remaining is with this single 4. I pop this out and I push that into my answer. And since there is no child of this node, we don't push anything into the stack, and now a stack is empty, right? And if you carefully observe what you have in your stack, if you just pop that out, 4 6 5 2 8 7 3 1, and okay, so if you pop this, so you would get these sequence of elements, and if you observe carefully, it is exactly what you got in the recursive solution. Okay, so were you able to understand this? I hope so. I would suggest you to go through this method once more so that you will be able to understand what I'm trying to do. Now let's look at the simple example. Okay, so what I do is I take 1 into my stack, that is the initial condition. I pop this, I place it into stack 2. Now I take all the neighbors of this and I push this into the stack 1. So stack 1 has 2 now. Now what I do is I pop this element from here and I place this here. And what I do is I push all the neighbors of 2 into the stack 1. So now I have 3 into my stack. Now I just 3, place it into stack 2 and push all the children of node 3 into the stack 1. And now since there are no nodes, we just don't push anything into the stack. And if you see, the stack 1 is empty. What you have in stack 2 is exactly what is the post order traversal. So I hope you were able to understand this. And let's look at the code. So as you see, we have to initialize the base case, which is if root is null itself, right? We are pushing the root into stack 1, right? So if the root is null itself, we just return the empty list because there is no tree to look. Now I create 2 stacks, stack 1 and stack 2. What I do is I create an answer vector that will allow me to return the answer. So what I do is while stack 1 is not empty, I initialize stack 1 with root first of all. While stack 1 is empty, I push that into stack 2, whatever is at the top of stack 1, and I remove that element from stack 1. Now the top element at stack 2, I push both of its children into stack 1, and I do this till the time stack 1 is not empty. Once it is empty, we know that we have our answer in this stack 2, and what I'll do is I'll just push back whatever is the topmost element in stack 2 and I just pop, and in the end I would have my answer stored in the answer array, and that is what I would be returning. So yep, this is working extremely well. If you see, it beats about 100%. So I hope you were able to understand this, and thanks for watching, and I'll see you in the next video.